Yeah, so I'm going to use this presentation to introduce a little bit myself. So my work can be placed in the area of algebraic specification, which is one of the most promising, let's say, approach to formal methods. So the formal methods assist the development of software and hardware systems at several stages, such as specification, verification, maintenance, evolution. I focus mainly on logical foundations for developing formal methods techniques. And I design software tools which provide support for the formal verification of systems. So today's talk is a part of a project which has the goal of providing a mathematical foundation for software systems with reconfigurable features. Reconfigurable systems are applications that work in different operation modes called configurations, and they react flexibly to internal and external stimuli for optimizing their performance. So my work can be placed here. I hope you can see my cursor. You do, right? Okay. So my work can be placed here. And this powers the development of formal methods. Basically, you design a language which implies an underlying logic plus some language construct. On top of that, so in order to do that, you need to some investigation, model theoretic studies and proof theoretic support. After you design the language, you design the formal methods techniques on top of the language, and then you use that formal method, to conduct case studies, and this can be medical devices, driver applications, intelligent transportation systems, cloud systems. These are all examples of reconfigurable systems which are used in safety critical areas. So in order to ensure that they work properly, there is no other choice but using a formal method. What I would like to add here is the fact that, at some point, reconfigurable systems were considered the next step on the evolutionary scale of software systems, And if you think in that way, then you cannot create next level software without creating, let's say, next level logic, So this work, which is the foundation of the developing such software, is crucial if you think in that way. Okay, so enough about my project. Let's at least explain a little bit the title of our talk, of today's talk. Well, as you probably already know, in 1920, Tarski gave a formal definition of what it means for a sentence to be true in a model. He clearly distinguished syntax from semantics, and he defined the satisfaction relation between them, using, of course, the interpretation of terms into models. In order to prove that a sentence is a semantic consequence of a set of sentences, one needs to check that every model which satisfies the set of sentences satisfies also the sentence. Well, since the collection of all models over a signature is a class, okay, it is difficult to establish if a set of sentences satisfies a sentence. So we need a finitary procedure. So in the literature, as you probably know, entailment systems are built for proving sentences from sets of sentences. Well, soundness means that each proof is valid and it is easy to check. Completeness, on the other hand, means that there is a proof for each instance of the satisfaction relation, and it's much more difficult to establish than soundness. So this talk is about this completeness. And of course, my results include also soundness and compactness. And probably you can derive also a downward Löwenheim-Skolem property for these hybrid logics. Okay, so hybrid logics are a brand of modal logics. So modal logics, as you already know, are constructed in general from a base logic. In the literature, there is a process defined at the institution independent level that takes a base logic and provides you a modal logic. So the distinctive semantic feature of modal logics are these Kripke structures. So basically the semantics, you can see it as a multigraphs. So these are nodes, you have nodes and edges. And the nodes are indexed by the possible worlds, and the nodes themselves are models in the base logic, and they are connected through some accessibility relations. And hybrid logics are equipped with a syntactic infrastructure which allow references to possible worlds. So that increases the expressivity and brings hybrid logic closer from the point of view of modal theoretic property, closer to first order logic. So the history of hybrid logic goes back to Arthur Prior's work back in 1967. So I have hybrid logic and I'm forcing. I use forcing. I introduce basically forcing to hybrid logic. So forcing, it's also a very old method of constructed models based on consistency result. It was invented by Paul Cohen to prove the independence of continuum hypothesis from the other axioms of Zermelo-Frankel's set theory. It was introduced by Robinson in classical model theory, and Berwise and Kissler extended this theory to infinitary logic and used it to give a new proof of the omitting types theorem. In institution theory, it was introduced by some students to prove Gödel completeness results at the abstract level provided by the notion of institution. So, yeah, so this is about title. And I hope I explained myself, the title. So what follows next? We go into the details. So at each section, I introduce some explanations. So I tried to structure the presentation as much as I could. So in the following section, I will talk about the notion of institution, the substitution, which is an abstract description of mapping of variables to terms, reachable models. This is a complete characterization of the models with elements constructed from basically with elements which which are denotations of terms. And basic sentences, this is an institution-independent description of the sets of atomic sentences of some important, some important institutions. When I say important, that means they are used in the area of formal methods, or they have a very developed model theory behind it. Okay, so the notion of institutions, which formalizes the intuitive idea of logical systems. I will say this includes the syntax and the semantics and the satisfaction relation between them. In algebraic specification literature, there is a standard practice to have an institution as a mathematical foundation for each specification language. Well, such that each language construct can be expressed as a mathematical entity in the underlying institution. So concretely, an institution is a tuple, consisting of a category of signature, a sentence functor, a modal functor, and a satisfaction relation between modals and sentences, which is indexed by signature. Well, I will drop this index whenever it is clear from the context. And this satisfaction relation, for this satisfaction relation, the satisfaction condition holds. So the satisfaction condition is explained. It is expressed in the context of a signature morphism. So having a signature morphism, you have a sentence translation from the sentences over the signature sigma to the sentences over the signature sigma prime. And you have a reduct model, which is a forgetful functor, you know, from the models over the signature sigma prime to the models of the signature over the signature sigma, such that this satisfaction holds if and only if this satisfaction holds. So this expresses the fact that the truth is invariant with respect to the change of notation. So this model satisfies the translation of that sentence, is the reduct of that model satisfies the sentence. So you can find this for the people from the audience which are familiar with Lindström's theorem. This is expressed also in that what is called abstract logic, but only for inclusions. Okay, but it holds in first order logic in general, not only for inclusions, even if you have subjective mappings or whatever mapping between vocabularies this satisfaction condition holds. And the classic example of institution is first order logic, many sorted first order logic. So the signature consists of these triples, you know, sorts, function symbols, and predicate symbols. Okay, so modals interpret each of these. So interpret each sort as a set, each function symbol as a function, and each predicate symbol as a relation. So for functions, you have arities, which basically it's not a natural number, it's just a string of sorts, so which indicates where the arguments of functions are coming from. The same is a predicate. The atomic sentences are given as either equations, of course, T and T prime need to have the same sort, or as relations, where this is a symbol of relations. So pi is from P over here, and T1, Tn are terms. And to this, we apply Boolean connectives and first order quantifiers. Satisfaction relation is a Tarskian satisfaction based on the interpretation of terms. And there are some restriction of first order logic, some fragments. For example, what I call here rel, relational, is obtained from first order logic by restricting the signature such that the set of sorts is a singleton and the function symbols consist only of constants. Other restriction, of course, can be obtained. For example, propositional logic is obtained for first order logic by restricting a signature such that the set of sorts is empty. So if the set of sorts is empty, basically I have only propositional symbols. So these are just propositional symbols which hold or not into the models. Okay, so as I said, we have a notion of substitution which formalizes at the institution independent level, mapping of variables into terms. At the abstract level, we have no choice but to represent variables as signature morphism. So some special classes of signature morphism. And that's why a substitution, you know, it's a pair here. This one. Such that these two diagrams are commutative and the satisfaction condition for substitution holds in the similar way that the satisfaction condition holds for an underlying institutions. And of course, an example in first order logic of example of such substitution are first order substitution, which are represented by mappings of variables into terms. So this can be extended to these diagrams here. So this is the underlying signature. Sigma 1 is the extension of sigma with variable from x. Sigma 2 is an extension of sigma with variables from y. So you have, if you place these diagrams in first order logic and you replace sigma 1 with sigma x and sigma 2 with sigma y, you can see that all this holds. Basic sentences, which characterizes some properties of atomic sentences from models. So if you think about first order logic, so probably this definition will make sense. So a set of sentences in an institution is basic. So this B is basic if there exists a model MB such that the satisfaction of B by a model is reduced to the existence of an arrow from MB into that model A. So A satisfies B if there exists an arrow from MB into A. So if you think about first order logic, so an atomic sentence is T1 equal to T2, where T1 and T2 are ground terms. So who is MB? So MB is obtained by factorizing the term model by the congruence generated by that T1 equal to T2. So this is how you obtain this basic model MB over here. And you can do that for all like ground atomic sentences.
Sorry.
Yeah.
Can I ask something real quick?
Yeah, sure.
So this basic model, what is the definition? So this looks kind of like a free generated algebra, one of these things. Okay.
Yeah. Perfect. Exactly. I wrote it over here. So if B is a set of atomic sentences, so the basic model is obtained by factorizing the term model, the congruence generated by the equations in B, and interpreting each relation symbol pi in this way. So yes, it's obtained by factorization.
Can I ask a question as well?
Yes, sure.
So what happens if you don't have if you don't have constants? If
you don't have constants, then you do not have ground atomic sentences.
Yes, so you do not have the basic model.
Yeah.
Okay, all
right. Yeah, but so since our results will be developed in an extension of the original signature with an infinite number of Hankin constants, there will always be constants over there if you are worried about that. But yes, the answer, yeah. So this is a definition for ground atomic sentences. I don't need to say ground because atomic sentences are ground. So if you don't have constants, you don't have terms, and basically you don't have atomic sentences and you don't have basic models. Now for another key concept that is used to develop completeness, this is reachable model. So this is a complete characterization of models with elements that are denotation of terms. I will not insist on this definition. So it's also based on the fact that the variables, are expressed as can be captured with a signature morphism. So if you have a reachable model, whenever you have an expansion over an extension of the signature with variables, whenever you give some assign evaluations of valuation of those variables into your reachable models, then you always generate a substitution, right? Because you have X, you map into a reachable model, right? And that will generate a substitution. And this is how you capture the notion of reachable models. So the fact that any expansion along an extension with variables, any expansion generates a substitution. And you can check that. So this is the characterization with if and only if. So in first order logic, a model is reachable if and only if its element consists of the notations of terms. And now we go to the stratified institutions. So in here, in this section, I will explain the notion of stratified institutions, which provides a general approach to Kripke semantics. So this is a slight variation of our original definition, which was meant to reason about modal logics. So I modified it a little bit to reason about Kripke structures. And of course, the set of atomic sentences from hybrid logics will not be basic, but fortunately, they are locally basic. So we will see what that means. And this is the definition of stratified institution. So a stratified institution is in particular an institution. So you have signatures, you have sentences, and you have models, exactly, and you have a satisfaction relation. But this satisfaction relation is indexed not only by the signature, but also by models here. Yeah, so in addition to that, you have a functor from the category of signature into a signature of relations, and a natural transformation. What do these two extra mathematical entities do? So this one extracts from each signature the set of nominals and the family of sets of modalities. Yeah, so extract nominals and modalities, So in concrete examples, you will see that a signature basically consists of a set of nominals, some modalities, and some signature in the base institution. So this will be just this functor, will just be the forgettable functor. So maps this. And this natural transformation, so if I take, this is a natural transformation to the functor from this modal functor to the modal functor for relations. So if I take a signature, so I will use delta. Delta will range over a signature of hybrid logics. And if I take a signature delta, so this one will be a functor which takes the model and extracts its frame. So if I have a model here, which is a Kripke structure, this K delta will extract from M a set of states, well, worlds, which I denoted like this, and a family of accessibility relations, this one. So the model, so K delta M, I will usually denote by W, capital W. And this will consist of a set of states and a set of accessibility relations. And as I said, the locals, so instead of the satisfaction condition, I have a local satisfaction condition because I have an extra parameter here for the satisfaction condition, which is the state or the world in which I evaluate a sentence. Okay, so here will be a signature which I omit, but I will never omit the world in which this sentence is evaluated. And of course, as in case of institution, the local satisfaction condition holds. Okay, so the translation of a sentence is satisfied at a state if and only if the reduct of that Kripke structure along the chi, satisfies that sentence. So yeah, so the generalization, I would say, from institution to stratified institution is quite straightforward, provided that the one who is doing it has a rigorous education in category theory. Okay. And of course, for this, I have the internal logic, where I can define the sentence building operators for any arbitrary stratified institution. For example, so sentences in hybrid logics can be nominals like this one, k. So I will let k range over the nominals. Okay, when a Kripke structure satisfies a nominal at a state w, well, it satisfies when the denotation of k into m. So this is a relational part. The frame of m is w, right? So the interpretation of k into m is the interpretation of k into w, and that needs to be equal to w. So when this is equal to the interpretation of k into m, this is when a Kripke structure satisfies a model. So yeah. So basically here it's like an equation. So this was the interpretation of k into m is equal to w. Okay, this is the classical definition of which is taken from the literature. Now, in addition to modal logics, you have this operation which is called retrieve, and it switches the point of evaluation into a model. So if for example, the evaluation is done at the world w, and I have this sentence at k phi, okay? So this operator will switch the point of evaluation from w to the interpretation of k into m. Sorry, here should be a phi. It's a typo, okay? So this w, it's replaced by the interpretation of k into m, okay? What else is specific to hybrid logic? This store operator. The store operator gives a name of the current state, and then you can use it to refer to it further in the formula. So basically here m satisfies this. So what it does, you take w, and wherever you refer it to as z, that is w. So this is a model which interprets, it's the extension of this one, which interprets z as w. So basically nothing changes here, but the fact that z is interpreted into m as w. Okay, so this is why it's called store, because it gives a name to the current state, and then you use that to refer it inside of a formula. And the rest of the operations are common to all modal logics. And hybrid logics are expressive enough to to describe temporal operators. So for example, the operator until, so until phi1, phi2, which says that, well, this one holds at the state W if there exists a greater state W prime, such that phi1 holds at W prime, and for the all intermediate states between W and W prime, phi2 holds. So this is expressed as this, you know. You can check it, you know, but it's not that difficult to check. So you give here a name to the current state, and that should be W. You know, you can connect it to the W here. This Z is connected to a next state, Z prime, which corresponds to W prime. So this one must be satisfied the W, and here it says, okay, so if indeed that state, which is expressed here, it's between W and W prime, phi2 must be satisfied. So it's not that difficult to, once you figured out the semantics of this operators, sentence operator, it's easy to express until operator in hybrid logics. So the idea is they are very expressive here. And the classical example of hybrid logic is hybrid propositional logic. So the signatures are triples like this. So a signature consists of a set of nominals, a family of sets of modalities. So usually I will use here in my work, is applicable only to binary modalities. And prop here is a set of propositional symbols. And modals, yeah, of course, they are multigraph, but the nodes are propositional models. That means set of propositional symbols. So in other words, a Kripke structure can be expressed as a mapping, right, from the set of states into this class of models of propositional logic over the signature prop. Okay. The sentences are defined by the following grammar. So basically the atomic sentence can be either nominals or propositional symbols. And then I apply sentence operators. The satisfaction condition for propositional symbols is defined here. So this Kripke structure satisfies this propositional symbol rho at the state W if MW, which is a propositional logic model, satisfies rho. Okay, and the rest, the semantics of the rest of the sentence operators are defined here. So at an abstract level, so you can instantiate that definition to this particular case of hybrid logic. Another example of hybrid logic is a hybrid first order logic with user defined sharing. So this has been defined in the area of computer science. The signature, okay, will consist of a set of nominals, modalities, and basically the signature from the base logic, it's a first order signature for which I identify a subsignature of rigid symbols. Rigid symbols will be interpreted uniformly across the states. So roughly speaking, actually not roughly speaking, exactly, it's a first order signature which contain a subsignature of rigid symbols. And yeah, so the models are the usual Kripke structures in which all of these symbols are interpreted in the same way across the states. So it's natural. For example, you can think of these rigid symbols as natural numbers. Natural numbers are if you go between the states, you would like to have the same natural numbers. You don't like the model to change the interpretation of natural numbers, or you have Boolean values, right? You want your true to be true in every model, and false to be false, and true will be different from false, and you would like for that to be interpreted uniformly across the states. As in case of hybrid propositional logic, so sentences are constructed from nominals and first order atomic sentences by using the sentence operators which I defined above. And of course, a Kripke structure satisfies a first order atomic sentences row if the first order structure MW satisfies row. So that is a definition. It is a classical definition, I think. And this is an example of hybrid first order logic with rigid symbols that I called, and this is proposed by me. So the signatures and the models are the same as for this institution that I presented previously. But the sentences, are constructed from equations and predicates. And in turn, these equations and predicates are constructed from so-called hybrid terms. So these hybrid terms are obtained from first order terms by applying this operator retrieve. Now think about a constant, right? If I have a constant in modal logic, well, in a hybrid logic, let's say. So if that is flexible, that means it's not rigid. So it's not here. So that will be interpreted differently in every node of the Kripke structure, right? And I have this operator which is applicable to the sentences. But actually this operator, I can apply it to the terms themselves. And the result, so if I apply it to a constant, at k of constant c, at kc. So that c, I will force the interpretation of flexible c. I will force it to be interpreted in the state denoted by k. So in this way, I can construct hybrid terms. And from hybrid terms, I can construct equations and predicates. Okay? So a hybrid equation will be like this. And predicates are of two types. Either I have P1, T1, Tn, if this pi is rigid, or I can have at k pi. So in this way, I will force my interpretation of pi at the state denoted by k. And then I can use the sentence operators, which I defined above, to define the rest of the sentences. So yeah, this is a major application of my work to this hybrid first order logic with rigid symbols. Unfortunately, atomic sentences are not basic. So this example shows exactly that. Because if you think of the basic set of sentences, because of the existence of that basic model, the satisfaction of atomic sentences, of ground atomic sentences, is actually preserved by the homomorphism, right? In first order logic. Or you can think of it in algebras, You have a homomorphism in algebra, an equation, a ground equation, and that satisfaction of the ground equation, it's preserved along the homomorphism. This example shows that this doesn't happen, in hybrid logics, in hybrid propositional logic. So I define here a homomorphism, which is an inclusion. And the satisfaction of K here is not preserved along this homomorphism. So this Kripke structure consists of only one world, one state, K. Yeah, so it consists of only one world, K, and the accessibility is just KK. You can see easily that WM satisfies K, you know, because these are the all worlds. The all states for W is K. So in all worlds, this one will be satisfied globally. So if I don't put here the parameter, that means it's satisfied in all states. So this will be satisfied in all states, right? But if I look at this model, which this Kripke structure is defined here, it has two states, okay, and one accessibility relation. This one, of course, I have to have this, otherwise this one will not be a homomorphism. And at the state W, this model doesn't satisfy K, and it doesn't satisfy as a row. So it doesn't satisfy globally K, and it doesn't satisfy globally rho. Okay. So fortunately, the set of atomic sentences, any set of atomic sentences in hybrid logic are not basic, but are locally basic. What does it mean for a set of sentences to be locally basic? So B is locally basic, is this retrieve B is locally basic. So, and if retrieve B is basic, and retrieve B is obtained from B by applying the sentence operator retrieve. So for each sentence here, I apply the an operator retrieve, so such that I force basically the interpretation of each B into some state. And by doing that, the result is a basic set of sentences. Okay, and this I will call that the B itself is locally epi-basic. And this will be used to prove my desired results, because from a locally epi-basic set of sentences, I can obtain a basic model, which is crucial for proving our results. Unfortunately, I took a lot of time to present this, so I still have two sections to present: forcing and the completeness. So in this section, I will present the forcing property, which is composed of a set of abstract conditions compatible with the local satisfaction of atomic sentences. As in classical case, a forcing property will generate a forcing relation. I also define the notion of generic set, which roughly is an increasing chain of conditions used to build a reachable model. And the generic model is a concrete realization of the generic set. Basically, the connection between these two is done by the so-called generic model theorem. And this is a framework in which I prove my results. I will not insist on it, since I don't have so much time left. I believe that the conditions which I enumerated here are easy to check in concrete examples. So the most important one is this one, that at the abstract level, you know, at the abstract level, I assume a subfunctor here, send 0, which will, in concrete examples, will give the atomic sentences over which the full sentences are constructed. The main idea is to separate what is specific to a hybrid logic from the feature that can be found at all hybrid logics in order to prove the desired results at an appropriate level of abstraction. So that is the reason, among other things, we assume here as a sum functor send0, which I said is used to build complex sentences by means of Boolean connectives, quantification, retrieve, and store. I denote by SB the restriction of SI to sentences obtained from the sentences of SI. So yeah, so this is, I mean, the restriction to a class of sentences by applying at most one-time retrieve. So my basic level consists of the restriction of SI to sentences obtained from atomic sentences by applying at most one-time retrieve. So for that level, I assume completeness, and I prove the completeness of complex sentences by making this assumption at the abstract level that the completeness for the basic level holds. Of course, when I instantiate my results, I have to develop entailment systems for the basic level of concrete hybrid logics. But at the abstract level, I just assume completeness for the basic level. Okay?
Sorry, Daniel, real quick question there. So that means that in order for you to get this result applied to a particular, let's say, hybrid logic or whatever, you would have to show first that that logic satisfies this completeness for the basic set of sentences, correct?
Yeah, in order to instantiate my results, so I need to basically to develop completeness for the basic level of that concrete hybrid logics. And this is how I show that my results. So at the abstract level, I have no other choice but assuming the completeness of the basic level. But when I say, okay, my results are applicable to this, okay, so then prove the completeness for the basic level. So I have to give some proof rules for the atomic sentences.
That makes sense. That makes sense.
Yeah. So this is what I do. But yeah, I simplify the problem greatly, right? Because it's relatively easy to obtain completeness for the basic level of any logic. So basically,
so I mean, the basic level would almost be, I mean, almost a propositional kind of completeness proof.
Yes, yes. So if you think, for example, the same idea is applied in first order logic. So I assume in order to prove completeness for first order logic, the first step, let's say, I'll prove completeness for atoms, for ground atoms. Okay? And starting from there, I prove completeness for everything. And the first step is, let's say, institution dependent. And the second step is institution independent. But this is quite natural, right? Because what gives the individuality of a given logic, it is their atomic sentences and the models. The rest, you know, they are similar. The semantics of sentence building operators, you know, they are defined uniformly at the abstract level. This is common for all logics. For example, in first order logic, what does it mean that the model satisfies phi1 and phi2? So that means I take, okay, I need to check that phi1 is satisfied by that model, and then I take phi2 and that should be satisfied. So that doesn't depend on the internal structure of that definition doesn't depend on the internal structure of the sentences. So based on that idea, I developed these results. And this is a definition of forcing. If you look at it, it's almost the same as in classical model theory. So a forcing property is just a triple, where this is a partial order set with a list element. Its elements are called traditionally conditions. Of course, if you have this, and this is a mapping, from F to the set of basic sentences from the logic. And you have, in addition, this compatibility of the conditions with sentences from the basic level. So FP satisfies at K phi. If this happens, then at K phi must belong to FQ for some condition Q, which is greater than P. But if I remove this, from this definition, this is the same definition of forcing from first of the logic. Well, this one is given, the definition of this forcing property is given at the abstract level. But yeah, so what is added on top of the classical definition is this operator, but K. That's it. I don't have anything else. So it's quite easy. Well, what follows next, the forcing relation, because each forcing property generates a forcing relation. Well, it's slightly more difficult than in the classical level, because in classical modal theory, this is a forcing relation which is generated by a forcing property is not indexed by the set of words, because you can think of first order logic as logics with one state, so this one is not indexed. But because here we have a set of states for each model, so the forcing relation will be indexed by binomials. And you can generate it like this, very straightforwardly. Once you realize this, the forcing relation should be indexed by nominals, that everything comes natural after that, So in order to have the fact that this condition P satisfy phi at K, this happens if and only if retrieve K of phi belongs to FP. So if this, this sentence belongs to the mapping of, so P is mapping to some set of sentences at the basic level. So this one happens if this belongs to the image of P into the basic level. And of course, you have this changes the point of evaluation. So from K, because I have retrieved K1 here, I changed from K, I changed to K1 here. Negation is classically defined. What is also interesting here is perhaps this definition here, the diamond phi. So this happens if this one belongs to the image of P into the basic level. So somehow I need to consider this diamond lambda K as an atomic sentence. So this must belong to the basic level. So this is the only compromise that I make, The sentences of this form, I have to consider them, well, just for the intuition, I said that this functor must map signature into set of atomic sentences, because because this definition is categorical. I can instantiate this with whatever I want, But in general, yeah, this should be atomic sentences. But if you think in that way, then you should consider this as atomic. Well, this one is not atomic if phi is different from a nominal. But if you want to develop the results, this one you need to consider as atomic. So this is the only compromise that I make. But I want to emphasize something else. Here, for this abstract level, I only assume that my logic is close to negation and retrieve. My logic doesn't need to be to be closed under quantifiers or possibility or under store or any other Boolean connectives. It just needs to be closed under negation and retrieve. So it is applicable to hybrid logics which do not have quantifiers or which do not have possibility or which do not have store. Okay, so this is defined if and only if this one exists. If it doesn't exist, then this one is ignored. So this definition should be understood as if this one is a part of my abstract framework, then the forcing P forces this at K if and only if. But if it doesn't exist, so this one should be disregarded. And I have also the notion of generic set, which is defined almost the same as in the case of a classic in the classical case. Yeah, so a set is generic if it, these three properties hold. So basically, if I have P belongs to the generic set, anything that is less than P, any condition that is less than C belongs to the generic set as well. If I take any arbitrary conditions P and Q, then I can find a greater condition R into J. Of course, this one is generic, it's called generic because it's either satisfies a sentence or it either forces a sentence or it forces its negation. Well, at some nominal K here. Then you have the notion of generic model, which is basically a realization of generic sets. So by the definition, you know, a model is generic for a generic set G. M is generic for G. If whenever this one forces something, well, sorry, I used a wrong notation, it should be a phi. So this one satisfies it, you know. So I have this. And the generic model theorem just connects these two definitions. And it said, okay, under mild assumption, every generic set has a generic model, which in additional is reachable. Okay, and then the completeness comes here. And in order to prove completeness, I have to provide a concrete forcing property. So that is defined abstractly, right? So a forcing property is a structure which satisfies those sentences. Well, in order to prove completeness, I have to provide that forcing property. In order to provide that forcing property, I define entailment systems. So an entailment system is a structure like this. So it consists of a category of signature, a sentence functor, and a family of entailment relations, such that all these the properties are satisfied. So this monotonicity, you know, transitivity. So this is a property is cut, you know, if you think it upside down. So this phi 2 over here is a set of sentences which cuts, you know. You have, this is a lemma that you need to provide in order to prove that phi 1 entails phi 3. One thing that I want to emphasize here is the fact that this entailment relation is between set of sentences, not single sentences. Okay.
Sorry, Daniel, real quick. So that entailment relation is in terms of, you know, like some sort of conjunctive reading there, right? So it's like if all the phi's, if I have all the 5, I can get all the 5, sorry, 5, 1, then I can get all the phi too, right?
Yeah, so it should be read that if this holds, then this holds, right?
Yep.
You can think of this as a proof rules, you know?
Yeah, but if I were thinking about it as proof rules, the way that I would interpret this is that I would read conjunctively the consequences, right? Not disjunctively. So it would mean that if I have...
Yeah, so this should be read conjunctively.
Okay.
So if this holds and this holds, then this holds. If this holds, then the translation of phi through chi, you know, will entail the translation of phi 2 to chi. So yeah, you should be as a conjunction, not disjunction. I don't, I'm not familiar with that kind of approach when the upper part is interpreted as a disjunction. So
no, Daniel, can I just interrupt for very brief? It was it was just that all the sentences in phi 2 are read conjunctively.
Exactly. Yeah.
That's the question, and this is what it is. Yeah. So the turnstile here means that from everything in phi 1, everything in phi 2 follows.
Yes.
Yeah. That was the question. Yeah.
Single turnstile, you can think as a double turnstile. And if you think in that term of satisfaction, but because this one needs to be sound, right? So if I replace this with the turnstile, this has to hold. So in case of turnstile, well, I said at the beginning, you know, well, but yeah, it's confusing, you know.
It's just because, I'm sorry, really, but it's just because, probably because you called that transitivity rule cut. Then people familiar with Gensen systems may think in terms of Gensen systems, and in Gensen systems, this turnstile would be read disjunctively on the right, conjunctively on the left, but disjunctively on the right. This was the
I see.
But everything else is
you know, I call this transitivity, not cut. In my defense, you know, it's a small joke. But thank you for clearing this up, because it always creates confusion. And actually, when I hear somebody else's presentation and they don't mention these kind of things, I'm also getting confused, because I always interpret this as in a conjunctive way.
Yeah, don't worry. Actually, just, you know, as a historical note, actually Bolzano read that conjunctively. You know, like he thought that there should be this sort of, you know, conjunctive reading of the set of consequences of a set of assumptions.
Okay. Yeah. So, as I said before, in order to develop completeness, we need to assume an internal system for the base level. And this is what we do. And furthermore, in order to define a concrete, well, it's not so concrete, but yeah, so a forcing property. So yeah, it is concrete at this level. Even the stratified institution is abstract. The forcing property will be concrete for this abstract stratified institution. So I need to assume that this internal system for the base level is complete. So actually the results do not hold if this one is, well, for the safety, you can think of this, okay, it can be, this one can be exactly the satisfaction relation, you know, and that will solve it. Of course, this is useless in applications, but from the theoretical point of view, it works. So we'll just replace this single turnstile with double turnstile and consider just the sentences at the basic level. And of course, you will have completeness, right? And the entailment system for complex sentences is obtained from this one by close it to some proof rules, which I will present it next. Okay, and these are the proof rules for satisfied logics. So they look like this. Again, this should be interpreted as a conjunctive. Conjunctively, what are the strange ones here? I think this one is the strangest. because it has a side condition, and this side condition is semantic. But actually, somebody suggested me to put here that this chi, this signature morphism, belongs to a class, and I can instantiate that class to the so-called conservative signature morphism. So conservative signature morphism, it is reflects basically the satisfaction condition. So in my case, so you can think of this as inclusions. Classical logicians, they always think, okay, if I have a signature sigma, I extend it with a set of, let's say, Hankin constants. And of course, the satisfaction in sigma is equivalent with the satisfaction of in the extension of sigma with that set of Hankin constants. But while this is a reasonable assumption, if one considers that the models do not have empty carriers. But if you consider that your models have empty carriers, actually it is not true. It fails. So think about it. So yeah, even in single sorted case, you know, I have a signature which doesn't contain any constant. Is it true that for all, I don't know, for all x different from x is not satisfied, is inconsistent? It's not true. The model with the model with the universe that consists of empty set actually satisfies this. For all x is different from x. You can check the definition. You know, it says for all the evaluation of x into that model, I have to check the fact that x is different from x. But actually there is no evaluation. And if there is no evaluation, since the sentence is for all, the model with the empty carrier actually will satisfy that by the definition. Unfortunately, my results are also applicable to the case where the models, I have to assume that the models consist, have non-empty carriers. To extend completeness to logics that allow models which may interpret some sorts as empty is non-trivial, okay? And that's why I have this rule here, cons, which also holds in the which holds only in the classical case. So it says, okay, if actually inference entailment holds in the rich signature, then it holds also in a less richer signature. And all the other proof rules, I believe they are natural. Even there are many, if you take each one of them and analyze it, I think they're reasonable. Okay, I don't have too much time. I think I already, well, I'm sorry for the time.
It's okay, we're over already, but I think you're close enough to the end. I can see there's only 5 slides left. Let's, I think we should finish.
Okay, I'm really, well,
it's
that's
okay.
That's a result of the fact that I didn't have time to prepare the presentation. So
it's on me. It's my fault. Yeah, I take the blame.
Okay, so this is the definition of the stratified entailment system, as I said. So you assume the entailment system from the base level, and then you close it, you know, to these proof rules. So basically, the way you define it, you define it the least entailment over this, the entailment system as the base level, closed under the proof rules, which I defined in the previous slide. And here it is defined the canonical forcing property, the concrete forcing property that I talked about. And the canonical force and property, I don't know why I call it canonical. I think it's a poor choice of words now. But yeah, because it seems so obvious for me. So I say, okay, it must be canonical. This concrete forcing properties is defined in an extension of the original signature with an infinite number of Hankin constants. At the abstract level, this extension is expressed as a colimit, actually as a directed colimit, you know. I think I made also a typo here. So a colimit, so in order to define a colimit, you need to define the domain category, and this is P alpha, and here should be a C. That C should be here. So the set of all subsets of C of cardinality strictly less than alpha, where alpha is the power of delta. So the power of delta is the cardinality of the set of sentences over delta. So this is how you introduce the Hankin constants, right? So you take the cardinality of the set of sentences, and let's say that is alpha, and then you add a set of fresh constants to your signature, right? And you develop your completeness results over that extended signature, right? So here you have a context in which you have delta, you have alpha, the power of delta, and you have a set of Hankin constants, which are ordinary constants actually, of power alpha. And this, you know, is a colimit, you know, of this functor over here. So this maps each C, each set of constants of cardinality less than alpha, let's say sigma prime, into delta C, let's say delta C prime. And this one is obtained as a colimit of all this. So basically you put them together over there. And having this defined, you know, then you are able to define your canonical forcing property concretely, you know, and which are the conditions. This is P over here. So the conditions consist of set of sentences over the signature delta C of cardinality strictly less than alpha. Okay. So these are my conditions. These are my elements here, over here. Who is this less equal relation? Well, it's the inclusion between those set of sentences. So it is the inclusion. And F, well, F, you obtain it, the mapping F, you obtain it by intersecting P with the basic level. And this is a canonical forcing property that I need in order to prove my completeness result. It's not so difficult to define. Actually, it's quite simple. Consists of consistent, but consistent here means syntactic consistent. That means they do not infer bottom. You know, this is not semantic consistency. Otherwise, I cannot use. So it's obvious that I need to use some syntactic consistency. So this canonical forcing property is based on syntax. And I use the generic modal theorem to connect this syntax to the semantics. In order to do that, I need this theorem, this canonical forcing theorem, which basically said that if I have a generic set, you know, over in the context given by that canonical forcing property, then every sentence which belongs to that generic set, belongs means, okay, you have a conditions and you have a condition which contains phi. So that means that belongs to that generic set. So it means, but for all the sentences in that generic set, you know, and all nominals, then that generic set eventually forces, you know, phi. So whatever you find in here, so it is forced by that generic set. So so under the hypothesis of generic model theorem, so there exists a generic model for G, which is reachable and satisfies each condition P in G. So this is actually the result that I need to prove completeness, and this actually links the syntax with the semantics. This canonical forcing theorem, which I called in this way. And from here, yeah, so my abstract logic is complete. And these are the proof rules for hybrid propositional logic. And if you look at them, they're quite simple, right? Because any set of sentences, you know, satisfies at kk. Basically, here is an equation. This equation says that k is equal k. So this one is the reflexivity. This one says that if k1 is equal to k2 and this one holds, right, I can replace k1 with k2 here because these are equal, are proved to be equal. If you look at this one is not complicated again, because this one says k1 is equal to k2 and a row here holds at k1, then of course it will hold also at k2. Well, the proof rules for my logic is much more complicated. And the proof of completeness for this is significantly more difficult than this one, because here you have also sorts which are rigid, you have sorts that are flexible, and you have to mitigate between them. And yeah, the proof rules are much complicated. But because I have this stratified approach, I was able to prove the result. But I think if you give someone the problem as it is, or prove it, I think it will be mission impossible, because you have these proof rules and you have also these proof rules, and I don't know if somebody is, you know, mentally, you know, you have to be willing mentally to do this kind of proofs, and if you don't do it in a modular way, then the results of success are very, 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 very low, I think. So this one is obtained because the approach from institution model theory is modular. So institution model theory doesn't mean only abstraction, you know. It means also modularity. It means also finding the bare causalities between logic properties. So this, what I think with these tools I was able to prove completeness for this quite complicated logical system. Yeah, and this is all. And thank you very much for bearing with me for such a long talk.